Good morning, everyone. Welcome to the lecture on Reynolds experiment. A part of the lab component of fluid mechanics laboratory, postcode MW1004. And in this video, we are going to look after visualizing the flow using the Reynolds experiment. Our major aim is to visualize the flow and evaluate certain characteristics of the flow or regimes using the Reynolds experiment. Let's quickly get into the Reynolds experiment, and basically we have discussed about flow visualization. This basically used to demonstrate how the fluid or air moves around a model. Let's say that we have a pipe, and we are mostly interested in understanding how the fluid moves or inside this particular pipe. So here there's kind of a fluid that gets into the pipe, and it comes out. It's fine. So we are going to understand how the fluid basically is going to be done. Earlier cases we have discussed basically flow visualization for let's say one is to understand the velocity field, other one is the pressure field. So we are interested in flow visualization for these two fields, whereas we discuss such things in Halisha apparatus. But whereas in Reynolds experiment, we are going to characterize the flow, behavior, such as say that laminar, turbulent, based on the forces acting on them. The forces, let's say, one is the force that is driving the fluid, is the inertial force, and the force that is stopping the flow is the viscous force. Basically, we shall say that if you draw the velocity profile at any section of the pipe, you can see that at the center can have a maximum velocity due to the viscous effect and the boundary layer effect. So the profile would look like this, and profile would look like this. Okay, in a pipe flow. So we shall see that at the center you have a maximum velocity. I say that you represent the velocity along the x direction as u, and we say at the center you have maximum velocity. So, and obviously you have a shear force that's acting here. So, but basically what Knowles has described this as Knowles number, a parameter called as Knowles number. That's a play between two forces. The one is the inertial force, other is a viscous force. So what is the inertial force? We can say that rho mass of the fluid, rho v is the velocity of the fluid, and d is the characteristic dimension, which is the pipe diameter, which is the following. And what is the viscous force? We shall define that by means of mu, the coefficient of viscosity, the dynamic viscosity. So we shall characterize this in a method that when the velocity of the flow is larger, okay, and we cannot edit the viscous force. Viscous force is given in the Reynolds experiment, but we can only alter this particular velocity, because if you have a density and diameter of pipe can also be changed. Okay, only the parameter that you can play with is v and d, and most cases d is also fixed, and velocity is the only parameter that you are going to change. So let's quickly get into the pump. Pump takes the water and then deliver it to the tank, and then from which it flows in this pattern. And here is the region where we are going to observe how the flow is going to be, our observation region. It's a glass tube and the transparent tube, and the flow is coming here and getting out of here. So what we are going to do is we are going to inject kind of a dye. Here is a dye controller, and we are going to inject the dye over here. There is a exit of the pipe. There is a dye being injected, and we can able to see when the dye is injected along the flow. We can able to see how the flow is going to the dye moves along this particular pipe. Then we have a control valve to control the flow, and we have a measuring outlet here. So we shall keep a beaker here and measure what is the flow coming in, and any flow that is going over here, remaining flow water will after the observation will go back here, and if the tank overflows here, and also the water will be redirected to the sump itself. So this is the basic nature of the experiment. Since it's an internal flow, flow is confined by the regions or the boundaries. So we call this the internal flow. So we have even we can have a nodes being extended to the external flow also. But for this experiment, we will restrict to the internal flow, flow through the pipe. So this is the laboratory setup at our fluid mechanics laboratory, and here is the observation by Reynolds in his original paper. So here we say that the flow is said to be in linear motion, or we say that it's going slowly. So in this case, the flow is uniform, steady. So we call this is said to be a laminar flow. And when it is velocity is being increased, and he can see that there is a transition. A part of it looks like laminar, and after a region, he get something kind of a partially turbulent. I'm not saying fully turbulent; it's partially turbulent. And when he increases the velocity much higher, so it becomes chaotic, and kind of uniformity is lost. So this can be called as a turbulent flow. So basically, what is here is when the velocity is less, viscous force is given. We are not going to modify it. So we shall represent that Reynolds number is said to be rho v d by mu. As I said, d is the characteristic dimension diameter of this particular pipe. Mu is the dynamic viscosity. V is the velocity. Rho is the density. In our experiment, density is given. Density of the fluid, that is going to be water, and we are eliminating the density difference that is carried out by dye is not substantial, so we eliminate that. And what you have a control valve here. That control valve can help us to increase the velocity. And what is the parameter? Diameter is also given. That's not a variable, and viscosity of the fluid is also a parameter that is given. So obviously we shall write that by at lower velocity the flow would look like laminar. At a region of higher velocity you have a turbulent flow. So which indicates that inertial force increases rapidly, but the amount of viscous force is not going to change. It's a constant. So this have a lot of energy in the inertial force and the domination over the viscous forces. So you have a inertial force dominating over the viscous forces. So obviously the resulting is going to be a motion of chaotic motion. So we need but beyond this we need a qualitative number, okay, which is said to be a Knowles number. That number was identified by the experiments, okay. That's what we are going to do. So we say that the Knowles number is less than 2000, okay, and you shall get a this kind of a behavior, the laminar behavior. When the 2000 or 2300, it depends on the experiments, maybe a small variations. And when the Reynolds number is more than you know 4000, or you shall get this kind of maybe 3000 to 4000 region. You will get, or even more, you will get turbulent region between 2000 and if you precisely control the valve between 2000 and 2500, you shall able to identify this transition region. It's in either laminar or trying to shift from the laminar to the turbulent region, because the it's like the inertial force tries to dominate, but the viscous force no tries to bring it back. It's like something like that, a to and fro play. So that's why the behavior looks like this. So let's get into the observation quickly. So first is to understand this, we need to understand what is the flow rate. Okay, so that from which we can calculate what is the velocity. So this is the volume, and we know to identify what is flow velocity. So we shall easily substitute into the Notch number. First, we shall identify what is the volume of flow. And by means of a beaker, so we can able to identify what is the volume of water collected, as we have this X setup, and you can able to collect what is the volume of fluid from the small beaker, and we shall identify and note it here. And then the diameter of the glass tube, you can measure it by means of the gauges, the diameter of this particular pipe, this the observation pipe, and here we shall have a this pipe, the diameter of this particular pipe will be given, and then we have an area of the horizontal glass tube, which you can calculate from the diameter pi by 4d square, and then kinematic viscosity of water. We say that at room temperature, let's say that 25 degrees centigrade, or does kinematic viscosity. If we are using kinematic viscosity, we shall use this formula because rho upon mu is can be written by the kinematic viscosity, or else you can use it as a dynamic viscosity. Most people will make mistake here, so please consider this, and density of the water is 1000 kg per meter cube. So first one is to calculate the discharge to flow rate over a period of time. So what is the volume of fluid flowing over a time? So as you know what is the volume, and as you know what is the time taken, because we have a beaker, so we can able to identify what is the how much time it takes to fill up this particular beaker. For instance, I'll mark the height, so from which I can calculate what is the volume of, and then volume of fluid occupied, and how much time it takes. So this will give me what is the discharge. From this discharge, as you know that discharge is given by area times velocity, okay, and obviously area of this exit pipe, which is given by pi by 4 d square. Earlier already we have seen that, and discharge is known. You can calculate what is the velocity. So that's what given here. So once knowing the velocity, you shall write it down here. And now you can calculate, upon substituting this velocity, you can calculate what is the Reynolds number. Let's assume the velocity to be about 3 meter per second. Obviously, I believe this is going to be a turbulent in this case. Maybe zero point 0.3 we'll consider. If we may get laminar or turbulent, we'll see that. So this is the density of the fluid, and the velocity is zero point 0.3 meter per second. Diameter of the pipe, you can even write it as in this case it's 20 centimeter, which is 0.02 meters, and we have a kinematic viscosity of the fluid. So putting all these things, if you get a value of around 2000, which are less than that, you can call the flow is said to be laminar. In case if the fluid is having a Reynolds number greater than 3000, you can say that is a turbulent flow, turbulent fluid, turbulent characteristics, and between these two you can have a transition. So here is the most clear view of how you are going to collect the fluid. Here is the control valve. The purpose of control valve is to regulate your velocity to increase the inertial force of the fluid. Here is going to be a beaker. You can keep it here. A small beaker will be given. Here is the region of where you can able to uh, focus. Here is the beaker that will be given to you. Here is the script here. Here is the beaker for collecting small collecting glass. So here is observation. The observation which comes with the calculations as well. We have already discussed. In this case, 100 ml of water being collected in a beaker, and time is 100 ml collect. So we can keep the volume collected as constant. So we can see that for 100 ml, the volume over a time is t, and then the flow velocity meter per second, and an ounce number you can calculate. So what I will understand from this is when this in this case is the first one where you can able to identify that lower Reynolds number, and here is a laminar region. That's why lower Reynolds number, and the Reynolds number is little larger. Okay, and in this case, laminar transition, and we have a turbulent. So the understanding is Reynolds number laminar, and Reynolds number transition, and Reynolds number of turbulent. And we can see that low discharge or low velocity, which also indicates also indicate low inertial force. So in this case, what is a dominating force? Viscous force. In this case, which is dominating, it's a play between inertial and viscous force. It's more or less, uh, going further and back. That's why you have a wavy motion, something like this. And also here we have a larger inertial force. Okay, we have a larger inertial force, but it's already dominated your viscous force. So viscous force cannot do anything. uh, it has crossed the boundary. Okay, so it's almost chaotic or mixed. A lot of energy is there in the turbulent. One such example is when you travel in an aircraft. When you sit at the back of the fuselage, okay, if you get a last seat, back end of the seat, sometimes when the pilot would be or the captain would be giving instructions to wear your seatbelt, saying that we are going under a turbulent condition or turbulent weather, because basically this turbulent weather, when the wind can come and hit the airplane at any direction, and it's random in motion, the fluctuating component of the velocity. If you take the velocity profile, if I can able to plot the velocity. Okay, that's a mean velocity over a time. I can get a small variations. Let's say this is going to be almost laminar. That doesn't going to affect it. But in terms of if I'm going to plot over a period of time, what is the velocity is going to be, large variation you can feel, because in three directions, if you take V component, W component, will be a lot of energy be uh, expressed in the, because inertia was very large. These conditions we call as a turbulent condition. So obviously you can see that flight getting a kind of a speed breaker or something like a fluctuations on the back of, and it's not going to it's not a very crucial part. It's just due to the turbulent condition, turbulent weather, that turbulent wind field on the particular aircraft. So this, apart from it, is to show you how this flow in real experiments. You can able to see that the pipe in this case, yeah, here is the pipe, and here is the observation region, and there is a pipe, injecting the injected over here on the center of the pipe, because we introduced the center, because where the maximum velocity. Inertial force just dominating the viscous force in turbulent condition. Inertial force is, sorry, in the turbulent condition, inertial force is dominating viscous force, whereas in the laminar condition, viscous force is dominating the inertial force. And this same similar experiments that you can do it with the Hellish apparatus as well, as we discussed. So in this, we have a dye tank, the flow is coming here. Increase the flow velocity, and you can able to see how the flow is going through the section. So from which you can also understand what is the mass number. This is also possible where you have a larger test section, and this is how we can apply the Reynolds number, for external flow problems. This is one such example from our from our wind tunnel. I think it's not running. Okay, anyway, some additional information. So thank you very much, and please subscribe to our channel, Aerolab VIT channel. Thanks for listening. Thank you very much. And I would like to share my thanks and credits to our students of Aerodynamics Laboratory VIT channel. Thank you.